Hello, welcome to Increasing and Decreasing Functions and the First Derivative Test. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. Applications of differentiation comes to us from Chapter 3 of Larson's 11th edition calculus text. This is for UTEP, Math 1411. Section 3.3, Increasing and Decreasing Functions in the First Derivative Test. I had to break this up into two parts because there are so many slides for each one. I wanted to make sure that I didn't go too long and, quite honestly, bore you as we go along. So check out part 2 for more examples of what I'm doing here. Alright, so let's start with some definitions of increasing and decreasing functions. First of all, a function f is increasing on an interval if for any two numbers, x1 and x2 in the interval, x1 less than x2 implies f of x1 is less than f of x2. So if I were to draw that in right here, I have some x1 and some x2, and f of x1 is lower than, so less than, f of x2, so it's going to be an increasing function. Notice this is not or equal to, I was just underlining the f of x1, the inequality. A function f is decreasing on an interval if for any two numbers, x1 and x2 in the interval, x1 less than x2 implies f of x1 is greater than f of x2, and there's a typo in the book. And I've been using this for a year now, and it's the only one I've ever found, so good job, editors at Cengage. F of x1 is greater than f of x2. So, again, if I were to draw that, we have any two x values, x1 and x2, then f of x1 must be bigger than f of x2, so it has to be decreasing in order to go down. Increasing, decreasing function. So now we need to know, how do we know what a graph is doing and where it's doing these things? So let's talk about Theorem 3.5. I know, that's an awesome title. Let f be a function continuous on a closed interval and differentiable on an open interval from a to b. Now, if the derivative, the first derivative, is positive for all x in the interval, then f is increasing on the interval from a to b. And this actually should be an open interval from a to b. Increasing and decreasing has to be on open intervals. If the derivative is less than 0 for all x in the interval, then f is decreasing. So if the slopes of the tangent lines are positive, the function is increasing. If the slopes of the tangent lines are negative, the function is decreasing. The open intervals, because at a, the graph isn't doing anything, it's just there. But over an interval, an open interval, then we could talk about increasing or decreasing. Something's going on. It implies movement. If the derivative is 0, then f is constant on the interval, if it's 0 for all x in that interval. We won't see that very often. There are functions where it happens, but most of what we're going to be looking at is where the derivative is positive or negative. And of course, we will need to know a little bit about 0 if we have these two divisions of being positive and negative. So here's some guidelines to find the intervals of increase and decrease. Let f be continuous on the open interval from a to b. To find the open intervals on which f is increasing or decreasing, we're going to use these steps. We're going to find the critical numbers of f in the interval from a to b and use these numbers to determine test intervals. Remember, critical numbers occur when the derivative is 0 or the derivative does not exist. So we have to find the derivative. We're going to determine the sign of the derivative at one test value in each of the intervals. All right? After we have our critical numbers, we could set up intervals. We'll walk through that, don't worry. And then we'll use the theorem to determine whether f is increasing or decreasing on each interval. Here we go. So we want to identify the open intervals on which the function is increasing or decreasing, and our function is h of x equals 27x minus x to the third power. Our derivative is 27 minus 3x squared. As a polynomial, we know this derivative is defined everywhere. So to find critical numbers, I want to find where the derivative is equal to 0. If 0 equals 27 minus 3x squared, we add 3x squared to both sides, divide both sides by 3, and if x squared equals 9, I know that x is positive or negative 3. Positive or negative, don't forget both of them. So our critical numbers, here in red, -3 and +3. And those critical numbers lead us to intervals. And we have one interval from -infinity to -3. Yes, that's an ugly infinity, but we're going to go with it. -3 to +3. And +3 to +infinity. So we have these three intervals, and in these three intervals, we need test points. Because whatever happens with this one test point, -4, it'll be true for everything in this interval. Why? Well, I know the derivative is only 0 at -3 and +3. That means it can't change sign. It can't be between positive and negative in this interval. It has to go through 0 to change from positive to negative. So it has to be only one sign, either positive or negative, in each region. So that's why these test points, one value will work for the entire interval. I randomly chose -4, 0, and 4. I could have used anything from -infinity to -3.00001. I just took some easy values in the intervals. Now, with these test points, we always evaluate the derivative at the test point. So I want to know, is the derivative positive or negative? When I put in -4 to the derivative, 27 minus 3 times -4 squared, that's 27 minus 3 times 16. And I know that 3 times 16 is bigger than 27, so when I subtract it, my answer is going to be a negative. Notice, I don't care what the number is. All I care is that it's negative. H prime at 0 is going to give us 27, which is a positive value. And H prime at 4 is going to give us a negative for the same reason that H prime at -4 did. So I know in this interval from -infinity to -3, the derivative is always negative. Between -3 and 3, the derivative is always positive. And from 3 to infinity, the derivative is always negative again. So if we wanted to, we could draw what's going on here. Maybe I'll use green. Negative, so we know we're decreasing. Positive, so we know we're increasing. And then negative again, we know we're decreasing. And once we have those drawn out, it's easy to see now. Decreasing on the interval from -infinity to -3. Positive means it's increasing from -3 to 3. Decreasing again from 3 to infinity. Notice how I've lined up my intervals here. These are only x values. That's not a point. It's an interval of x values. And I can see that I have the entire real number line taken care of, so I know I'm not leaving anything out. Let's try it again. If y equals x plus 4 over x, the derivative is 1 minus 4 over x squared. Quick little reminder that 4 over x is the same as 4x to the -1, and that's how we find our derivative. One critical number where the derivative is undefined is when x equals 0. Notice that is not in the domain of the original function, but it's not in the domain of the derivative either. Set the derivative equal to 0. If 0 equals 1 minus 4x over x squared, add the ratio to both sides. 4 over x squared equals 1. I'll multiply both sides by x squared. My 0 is taken care of, so that's not a problem. X squared equals 4 tells me x equals plus or minus 2. Our critical numbers are -2, 0, and 2. So not what I wanted to do. I was hoping to highlight that. There we go. X values, critical numbers, -2, 0, and 2, making 4 intervals on our number line. Okay. So we have everything before -2. Here's a test point, -3. We have everything between -2 and 0. Here's a test point at -1. +1 and +3. Now remember, you don't have to use these values. Maybe your favorite number is 1/7. Feel free to use 1/7 as your test value. You cannot use -2, you cannot use 0, and you cannot use 2. You could use any other values in these intervals in order to get a test value. I just try to keep it simple. So when I evaluate the derivative at -3, I get 1 minus 4 over -3 squared. -3 squared is 9. 1 minus 4/9 is positive. 1 minus 4 is negative, and that happens twice. And 1 minus 4/9 happens twice as well. When we evaluate these in the derivative, we find the derivative is positive or the derivative is negative along the way. So what does this tell us? This tells us that if we're positive, we must be increasing. Negative, we're decreasing. Negative, we're decreasing. Positive, we're increasing. So it's easier now to write these increasing from negative infinity to 2, and again from 2 to positive infinity. Decreasing, to, negative 2 to 0. Where did my negative go? I seem to be missing a negative on here. That one right there. Negative 2 to 0 is decreasing, and 0 to 2 it's decreasing. Note, we have to exclude x equals 0. It's a critical number. So we can't just say it's decreasing from negative 2 to 2 because it's not decreasing at x equals 0. The function isn't even defined there. So make sure you take care of all of your critical numbers as you're labeling increasing and decreasing. And the first derivative test. This is going to help us find maximums and minimums. Let's let c be a critical number of a function f that is continuous on an open interval I containing c. If f is differentiable on the interval, except possibly at c, then f of c, the y value, can be classified as follows. If f prime of x changes from negative to positive at c, then it's a minimum. Why is that? Well, if we go from negative to positive, we're going to have a minimum. It's a low spot. If the derivative changes from positive to negative, we're going to have a high spot, a maximum. But if it's the same sign on both sides of c, whether it's positive or negative, we'll have neither a relative minimum nor a relative maximum. Something weird's going on there, something that's important, but it's just not an extremum. Alright, so let's take a look at a few examples of this. We're going to find the critical numbers. We're going to find the open intervals on which the function is increasing or decreasing, and then we're going to apply the first derivative test to identify all relative extrema. So, take the parabola, f of x equals x squared plus 6x plus 10. I can envision this in my head, so I know it should only have one critical number. This is a parabola that opens up. It should have a minimum. I know this minimum is at the vertex. There's a lot of things I know about this just from algebra. So our calculus should absolutely work on a, quote, easier function. Let's see. To find the critical numbers, we set the derivative equal to 0 or find where it does not exist. The derivative is 2x plus 6. As the derivative is a polynomial, derivative exists everywhere. The derivative is equal to 0 when 2x plus 6 equals 0. If I subtract 6, then divide by 2, I get x equals negative 3 as a critical number. Any test point to the left of negative 3, I'm going to use negative 4. Any test point to the right of negative 3, I'm going to use 0. Remember, we're testing these test points, the ones in green, in our derivative. I want to know if the derivative is positive or the derivative is negative. So when I put negative 4 in the derivative, I get a negative answer. I don't care that it's negative 2. I care that it's negative. When I put 0 in the derivative, I get a positive answer. I don't care that it's 6. That's cool. Nice. Way to go, 6. But it doesn't matter. We care that it's positive. So if I am decreasing to the left and increasing to the right, it makes sense that we're going to use the first derivative test to draw the conclusion that we have a minimum here. Just as we thought, because it's a quadratic. So let's see. We have our critical numbers at x equals negative 3. It's increasing from negative 3 to infinity and decreasing on the left from negative infinity to negative 3. Because it changes decreasing to increasing, x equals negative 3 is the location of a minimum. The y value always comes from the original function. So this negative 3, now that I have a critical number, the derivative tells me where to look. The original function tells me what is the value. So f of negative 3, when I evaluate my original function at negative 3, I'm going to get 1 as my y value. The minimum point is negative 3, 1. And if we look at a graph here, negative 3, 1 is indeed our low point, our minimum. It's decreasing to the left, increasing to the right. It's always nice to be able to see a graph to verify that we've done our calculus, our algebra correctly. Number 2, another polynomial, f of x equals x cubed minus 6x squared plus 15. I find my derivative. In order to find critical numbers, my derivative is 3x squared minus 12x. The derivative is never undefined because it's a polynomial. The derivative is equal to 0. All right, in order to solve this, I have two terms. I'm going to take out the greatest common factor, 3x, and I'm left with an x minus 4. If two things are factored to give me 0, two terms, multiply to give me 0, then either 3x equals 0, in which case x equals 0, or x minus 4 equals 0, in which case x equals 4. My critical numbers 0 and 4. Pick any value to the left of 0, any value between 0 and 4, and any value to the right of 4 as my test points. Now sometimes, because we don't care about the numbers, sometimes when we have a factored form, it's easier to test just the signs. And this is a sign chart. The 3 is always a 3. The x, well, depends on what we substitute, and the x minus 4. So when I substitute my x equals negative 1, I know that the 3 is positive, negative 1 is negative, negative 1 minus 4 is negative, and I don't care about the numbers. I care that positive times a negative is positive. And so I know that I am increasing in this particular interval. Again, when f prime is evaluated at x equals 1, I'll have 3 times 1 times 1 minus 4, and I don't care about the numbers, so I know this is positive. 1 is positive, 1 minus 4 is negative. Positive multiplied by a positive multiplied by a negative will give me a negative. And finally, when I evaluate the derivative at 5, I'll have a positive times a positive times a positive, and 3 positives make a positive. So I will have increasing. Evaluate the numbers, just look at the signs, or just look at the signs and ignore the numbers altogether. It doesn't matter positive, negative, as long as you have the sign, positive or negative, the value doesn't matter. So we can conclude that we're increasing from negative infinity to 0, and then we're decreasing from 0 to 4, and then from 4 to infinity we're increasing again. Remember, these are all x values telling us what's happening with y. Y is increasing, y is decreasing, but x values tell us where it's happening. Thinking about those images, since we switch from increasing to decreasing at 0, it's a maximum point. Remember, to find the maximum value, we evaluate the original function, and f of 0 is 15. And we know that at 4, we change from decreasing to increasing, so this will be a minimum point. 4 comma f of 4, that's the point 4 comma negative 17. Let's take a look at the graph, see if we're right. 0, 15 a maximum, 4, negative 17 a minimum. It looks like we were pretty right on with what's going on. It's increasing, and then decreasing, and then increasing. Good work. Don't forget to watch part 2, as I'm going to give more examples. If you need more examples that are not all nice little polynomials, definitely watch part 2. Thanks for listening.